Hi everyone and welcome to a new video about analytical controller design, and this is our example number 4, and we continue with the design of a lead controller using the analytical controller design method. We will again look at the calculations and we will verify our calculations using simulations. So let's look at our example number 4. So what we have is the lead controller design using analytical method, and we have the following diagram. We have the controller in cascade with a plant, and we have a unity gain feedback configuration. Now the plant is given by this expression. We have the 6 over s times s plus 2 times s plus 3. So we have 3 poles, one at the origin, one at -2 and one at -3. The controller is specifically given here as the lead, and we have 3 parameters, A0, A1 and B1. Now we will determine those 3 parameters using the given design specifications, and from there we will determine the design point, and then you will use the design equations step by step and going to these 3 parameters. So let's do that step by step. First, look at the design specifications. So we have these design specifications. We have the overshoot of less than 10% or 0.10, and we have a settling time of less than 5 seconds using 2% criterion. Now, what we want to do is, of course, work through the design point S1, as we did also in the previous videos. So for that, I can use the overshoot first. So the solutions overshoot will give me of 10%. I have now just made it at the edge, and I can now use the formula of the damping ratio and substitute in that the value of the overshoot as a scalar. So 0.10 in here and 0.10 in there. And if you do the math here, you will get very close to 0.6 or 0.591 a little bit accurately. Now the next one is the absolute damping, which is sigma, which will give us the real value of our design point. Now the sigma is given by 4 over the settling time will be 4 over 5. So I've again taken the settling time at the edge of our maximum value. That will be 4 over 5, 0.8. That will be the real part of our design point. That will be given shortly. We also have the imaginary part, and imaginary part is the omega d, which is a damped frequency, and it will be sigma times the tangent of arc cosine of the damping ratio. This is a formula we can of course derive, but I've just used this and also did that in the previous videos. I can do that of course in more detail, but the thing is that you really need to know that in graphical form that you can prove this. It is not really that difficult. So what we have is then the tangent of arc cosine or inverse cosine of this damping ratio, which is shown here. And if I now do the math here, you will get 1.09 radians per second for the omega d, and which is then the imaginary part. Now if I now collect these values, I can now make the expression for the closed loop poles, which are actually the dominant poles. So these 2 poles, S1 and S2, is given by minus sigma plus or minus j omega d, will determine the dominant poles, and we assume that we can approximate the complete system by these 2 dominant poles. So that is the expression minus 0.8 plus or minus j 1.09. Okay, now before we start, we make the controller a P controller, and we set the value even simpler at 1, and then take one of these poles as our design point. Now most of the time I will take this S1, which has a positive sign for the imaginary part, which is shown here. Now this is our input for our design equations. So I will use this, and then we have our design equations. Now before we jump to that, let's look at also to the formulas. So S1 is equal to the absolute value times e to the power j beta, which is now the absolute value and also the angle here. Now the value of this, of the absolute value, is then given by this real value squared plus the imaginary value squared, and then take the square root of that one. That will be 1.35. Now if I also want to calculate the phase, that will be beta, and since this is, if you draw this in the complex way, that will be clear shortly, you can see that the phase contribution is 180 degrees minus the arctangent of the imaginary part divided by the real part as an absolute value. And that will result in 126 degrees. Now, if you combine them together, you will have the S1 is equal to 1.35 as the absolute value and the phase of 126 degrees. 26 degrees. We have also, of course, the loop transfer function, which is given by L, and then L is then the expression from the diagram. So we have the controller and the plant, and that will have also unity gain feedback. So we have the controller times the plant times 1. It's actually shown here. And since the controller is 1 and the plant is given, I can now use this expression. And since this is 1, I can even make it simpler. This is the expression for our loop transfer function. I need this for our design equation. That means the absolute value of the loop transfer function evaluated at the design point. And I also need the alpha. So let's look at the phase of the loop gain at S1. So if I now look at the diagram here, you can see there's a design point S1, which is actually this design point, which is a real part of minus 0.8 and also the imaginary part of J1.09. Now this angle is what we have calculated here, so it is 126 degrees. You can also see that this is a positive angle, and we need to subtract actually from the whole circle this angle what we actually have done here. And this length from the origin all the way to the design point actually is 1.35. Now the phase of the loop gain at S1 is actually the phase contribution of the loop transfer function and evaluated at the design point. So if I look at the alpha, which will be then the phi 1, which is the phase contribution of the pole 1, phi 2, which is the phase contribution of the pole 2, and phi 3, which is the phase contribution of pole 3. So we have the pole at 0, minus 2, and minus 3. So those three phases must be calculated separately, and then we have to add them, and that will be, of course, in summation alpha. Now, since the phase contribution of a pole is negative, I need to also make this negative. So I will calculate phi, but I will make the phases negative. So let's calculate the phi 1. Phi 1 is this. It's exactly the same as beta, which is of course a coincidence because this is just at the origin. And that's exactly the same expression as we did for the beta. So we have 126 degrees. Now if I look at the phi 2, which is at this location, what I do is I use the arctangent formula. So it is the height divided by this distance. The height is still 1.09, but this distance is now 2 minus the 0.8, which is actually shown here. That is actually 1.2. So that is then calculated 42 degrees. Now for phi 3 in a similar form, it is still, again, you will use this triangle with a right angle here. You will have a height of 1.09. That is exactly the same as before, but the distance is now from 3 minus 0.8, which is shown here, and then we'll get 26 degrees. Now if you collect those angles together for alpha, you will have then the following expression that will result in a total angle contribution at S1 for the loop transfer function of minus 194 degrees. We also need the magnitude of the loop gain at S1. So what is the total length evaluated at this design point? Now, if I now substitute the design point in this expression for the loop gain, this is actually shown here. You can see that this is the S, this is the design point, S plus 2, which is shown here, and with the plus 2, and S plus 3, which is also the design point plus 3. I will now need to calculate the length of this one, which will give me the following expression. So it is 6 over the square root of the real part squared plus the imaginary part squared for the first term, for the second term, and also third term in a similar form. And this will result in 1.11 approximately. Now if I now combine the angle and also the length in this expression, I have now in total this expression for my loop transfer function. So I have now determined the necessary parameters to continue in the next phase. So let's look at the next steps. The next step is actually determine the lead control parameters A0, A1 and B1. So the parameters for the design equations are, again, so let's summarize this: alpha minus 194 degrees, beta was 126 degrees, the absolute value of S1 was 1.35, and the absolute value of the loop gain evaluated at the design point was 1.11. Now, what we have, we will see that shortly, we have two design equations, but three unknown. So we need to select one of these three. Now, most of the time we select the A0, which is actually the DC gain of the lead controller. So I will also do that in this example. As a DC gain of the controller A0, we select A0 is 1. So I will take it very simple, just unity. Then using the design equations, we will get the following. This is our design equation for A1. If I now substitute given values in here, and also for A0 what I have selected as 1, I will now have the following. Now if I now do that, just do the math here, you will get very close to 0.28. Now for B1 in a similar form, there's a design equation for B1 using A0 and all the parameters we have here. If you substitute that for the expression for B1 and you do the math, you will get very close to 0.097. So I have now, in summary, these three values. I have selected this one, and this is the calculated value using this A0. Now the expression for the lead controller was this. Let's refresh this, and then now substitute the values we have now given here. It will be the lead controller. Now if I want to rewrite this in a better form, such that I can see the real, the pole and the zero and also the lead controller gain more easily and directly, I can now divide the numerator and denominator by 0.097. I will do that and I will get the following expression. If I continue a little bit more, I can of course factorize the numerator here, so I can see the 0 also easily. I will also do that here. That's actually a next step. And I can see that the 0 of the lead controller is at minus 3.56 and the pole is at minus 10.3. You can see that the pole is farther away from the vertical axis than the 0. That means this controller will have a positive phase contribution, which is of course true for a lead controller. For a lag controller, you will have a pole closer to the vertical axis than the 0. So this is our designed controller. So we will now check if our system using this lead controller is performing as expected. So let's look at the MATLAB simulation results. So I've now plotted the unit step response of the closed loop system with the lead controller, glead, and this is what I get actually from the MATLAB using the exact values of A1, A0 and B1, etc. What you see is that it's a little bit different than what I had. So if I go back, you can see that the pole was at 10.3 and also the lead controller gain was 2.89 and the 0 was 3.56. Now if I now go back to the expression, this is 10.27, it was 10.3 in my case, so it is a little bit closer, but that error is due to my rounding F error. So this is more exact, and this is 2.88 approximately. I had 2.89. You won't see much difference in the performance. So if I now plot this unit step response of the system using this lead controller, I have this expression. You can see that the final value is 1, which is not really a surprise because we have a pure integrator or a pole at the origin, so your steady state value will be 1 for a step input. There's also a rise time of 1.4 seconds, but the thing is, we are of course interested in the overshoot and also in the settling time. So let's look at the settling time and overshoot. Overshoot is here 9.67%, which is less than 10%, which is fine. So of course at the edge, but it's still less than 10%. And I see that the settling time is 4.51 here. It is also less than 5 seconds. So I mean 4.51 seconds. So it is less than 5 seconds. So both criteria, both specifications are met actually with this lead control. So in the first round, we have actually met both specifications. So overshoot less than 10%, and also settling time is less than 5 seconds. That means we are done actually in this form with this design of this controller. You can improve this, of course. You can make also a little bit adjustment in the maybe the location of the pole, maybe the location of the zero, maybe both of them, maybe also the gain. You can do many things to make it even maybe faster, also make the overshoot a little bit less. That's all possible. Now I will do that now also briefly in the next step in MATLAB real life. So let's also look at that in MATLAB using the control system tuning method, which will be helpful also to see what's actually happening when I change a parameter of iController. So let's jump to that in MATLAB. So we are at MATLAB. So I have now developed a script. I have defined again the Laplace parameter for our lead controller design. This is my plant, which is shown here again with 3 poles, and this is our loop gain. Of course, in our original form, it is just a P controller with a gain of 1. Now we have the MP, which is our overshoot specification, also the settling time TS of 5. Now this is just the formula we have also used in the calculation section. Again, we use the zeta, sigma, and also the omega d, and also the design point. Now all of them are shown here, so I can calculate the alpha, beta, and also A1, A0, I mean S1, which is selected DC again. Now let's run this. We will see what's actually happening, and I can now type in, for example, here the zeta, just to check, which is actually what we had also. I can also check the sigma, which is 0.8. I can also do omega d, which is 1.09. All of them are as we have calculated, and this is the design point. I can also do alpha. So what is actually alpha? So if I now do alpha, I will get this one. This is of course in radians. So if I want to have it in degrees, I will do 1 times 180 divided by pi. So I will have then this. It is 165 degrees, which is actually also the same as the alpha what we had, because we had the alpha of minus 194 degrees. You can calculate this using this 360 minus 165, and it will result in what we have here. So it is very close to what we have, but it's just rounding off errors. Okay, that's all fine. Let's also look at the G lead, which is the controller, and I will do that in this form. And you can of course use also the zero pole gain model, which will actually give you this expression. So let me do that. So G lead will be G lead, and then you can see that it's indeed actually what we have, 10.3 approximately for the pole. We have the 0, and we have also the lead gain. Now if I now do here step, so T is the closed loop system, we have the feedback, and then this is the controller times the plant. The second entry is actually what we have in our feedback loop, which is just 1, and this is the third entry, which is which is actually for if it is a negative or a positive feedback. Now in most cases you use of course negative feedback. If you forget this third entry, the MATLAB understood this actually as negative feedback, but I will always place this to make sure that this is indeed negative feedback. Okay, if I now plot this, the step response, and I will also make the grid on, you will have the following plot. I will make it a little bit larger and also make the limit to maybe 8 seconds. You can see what's actually happening with the peak, exactly what we have discussed in the calculation section. And we have now 4.51 seconds for the settling time, and this is 9.67%. Now I will now also do that in the application of MATLAB. So if there is a nice application of MATLAB Control System Designer, I will run this, and we will upload now our controller, our plant, and everything, and we'll see what's happening when I, for example, adjust something in my controller parameters. So let's do that. So if I now run this, and I will get the following. This is our controller control system designer tool, what I have now is the following situation. I have the root locus plotted on the left and the step response on the right. There are, of course, also more plots like body plot, but we don't need that, so I have to get rid of that one. So I need to first import the transfer function of our plant and also the controller in my configuration, in my architecture. So I will first choose the configuration. There are many configurations shown here, so I will just select this one. This is the pre-filter, which will be just one in our case, so this is just one. This is our feedback block, but in our case it's just one, also one. This is our lead controller, so it is the C, and this is our plant. So I can of course type in just GP or G lead here, but I can also import this. So let me do that. Import the controller, G lead, import, and also the import of the GP. Import and then run. We can see that will result in this one. I will make the properties and I will just place this at 8 seconds. So you can see if I have the peak and also the settling time, you can see it is exactly the same as before. Okay, what can you do more in this one? You can just see here the following. If I now a little bit zoom in here, so I will zoom in here because this is actually where the action is. So I will zoom in here. And I will now define a region for my design. So design requirements, so right mouse click, design, and a new. One of the design requirements was of course 5 seconds. So 5 seconds, I will get a vertical line for my settling time. This is actually the region I'm not allowed to be for my close to poles. You can see that the close to poles are given by these pink dots. And if I also add the design requirements for our overshoot, which must be less than 10%, and I will add that also, you will have another forbidden region, and these two regions will overlap, and you will have actually this white region where the close to poles are allowed to be. And if I see this, these are the two dominant close to poles, so these are at the edge actually of our allowed region. So the design is very precisely done here. So if I want, of course, improve this, I can place the poles maybe a little bit to the right side by taking this one, or I can also move with this one. It depends what you prefer. This is the 0, and this is the pole of the, this is the 0 of our lead controller. So this is the pole of our plant. There's a pole here of our system at -2, and there is a pole here of our system, also plant of -3. This is the 0 of our plant. The lead controller, and this is the pole of our lead controller, approximately at -10.3. So this is what the specification is, and this is what you can use to make the situation more graphically visible. So if I now zoom in here also, a little bit zoom in here just even more, you can see what's happening. So it's really at the edge, and I can now say, let me take this close to pole and make it a little bit far away from the vertical axis. You can see that the overshoot is now decreasing. It is now 6% approximately. 6% approximately. So it is now 5.5, but the settling time is now a little bit larger than 5 seconds. So if I win here something, I will lose something here. So there's really optimum. So I can of course go back. That will make my settling times better, but of course the overshoot will increase. But still within the specification, so there is no problem. But it really depends on you what you prefer. So if you say, okay, I will go a little bit here, and I will have now, if I go down, you will see that the overshoot is almost 1%, and the settling time is just approximately 3.5 seconds. It is even better. Of course, that really also depends on what is available and what is possible in a real time. So if I just design something which has, of course, very high gain, that might be not practical. So you really need to check that also in the final phase. So if I go back again, this is what I had for my system at the edge. And if I go in the forbidden region, for example, in here, you can see I'm over the overshoot, which is of 10%. If I go even further, the settling time will also go down, because go over the 5 seconds, because now this vertical line will be also crossed. So I have now again problem in the overshoot and also problem in the settling time. So both of them are not met. This is a very nice tool. So use your root locus plot and with the design the region to see where the closed-loop poles need to be. So if I place it back, I can set it here, and this is maybe a better solution since it's at the edge of the settling time, but this is a little bit less overshoot. That really depends on your application. Okay, this is our fourth example about the analytical design of the lead controller. Again, very detailed analysis using the simulations also and a calculation. I have done this purposely, show this in MATLAB, how you can do it also by yourself. If you have questions about this, just let me know and I will try to answer them as soon as possible. Thanks again for your attention and time, and see you next time, and take care and have a nice day.